Chapter 24, Probability and Statistics. Section 24.3, the method of Lagrange multipliers. The method of Lagrange multipliers is often used to optimize a multivariable function with constraints. Here we study a simple example using the method of Lagrange multiplier to optimize our function under a constraint. Let's minimize this function given this constraint. The constraint is this: x plus y plus 2z plus 2u equals 9. We need to rewrite this constraint in this format: x plus y plus 2z plus 2u minus 9 is 0. We first define the Lagrange function, or so-called Lagrangian, L. L is the function to be minimized here, minus this alpha is a parameter, or it's called Lagrange multiplier, times the constraint. This constraint is always 0. X plus y plus 2z plus 2u minus 9 is always 0. So really L is the function to be minimized, minus alpha times 0. To minimize L, we use the typical method. The first derivative of L with respect to x, y, z, and u should be 0. That's what we do here. dl over dx is 2x. From here, minus alpha. From here, it should be 0. dl over dy should be 0. It's 4y, and then minus alpha, it's 0. dl over dz is 8z. From here, and then minus 2 alpha. From here, it should be 0. dl over du should be 0. And these four equations must hold true regardless the value of alpha. So to minimize the Lagrangian L, we have x is 1/2 of alpha, y is a quarter of alpha, z is a quarter of alpha. From here, u is 1/2 of alpha. Now because of this constraint, we know x plus y plus 2z plus 2u should be 9. And then we can plug in the expressions of x, y, z, and u in terms of alpha, and we determine the value of alpha. Alpha has to be 4 to ensure this constraint is true. We then get the values of x, y, z, and u easily because they are expressed in terms of alpha. We just plug in alpha equals 4 here, here, and here, and here, and x, y, z, and u are 2, 1, 1, 2. We plug in the values of x, y, z, and u into this function, where c, the minimum value, is 18. Now you may ask, what if we do not have the constraints? Well, it's pretty simple. The minimum value should be just 0. When x, y, z, and u are all 0, this function is minimized with the value of 0. With this constraint, well, the minimum value is 18. So you may also try some other possible values. What if x is 9? All other 3 are just 0. You can plug it in when x is 9. Well, you just plug it in. 9 squared is 81. That's definitely greater than 18. You can try some other combinations. You can say, well, maybe this is 3, and this is 1, and this is 1, and this is 0, stuff like that. You plug it in. You'll get a value greater than 18. Now let's look at another example, problem 24.3.1. Use the method of Lagrange multipliers to minimize another function. And this time we have two constraints. X plus y plus 2z minus 5 must be 0. X minus u minus 1 must be 0. Now we have two constraints. We need two Lagrange multipliers, alpha and beta. So L is defined to be the function to be minimized, and then minus alpha times this constraint. So x plus y plus 2z minus 5 must be 0. X minus u minus 1 must be 0. And I put two Lagrange multipliers in front of this 2. Now I'm going to do dl over dx should be 0, dl over dy should be 0, dl over dz should be 0, dl over du should be 0. And then from this equation, we see x is 1/2 alpha plus 1/2 beta. From this equation, y is a quarter of alpha. From this equation, z is 1/2 of alpha. From this equation, we have u is negative beta over 4. So again, you just need to know just simple derivative calculus operations, and then you can get this. You express x, y, z, and u in terms of alpha and beta. And remember, we have two constraints, so we plug in the expressions of x, y, z, and u into these two constraints. We have this, two constraints. Alright, so this is x, y, and this is this is x, this is y, this is 2 times z equals 5, and x minus u is 1, so this is x minus u, which is plus a quarter of beta, is equal to 1. So look, we have two linear equations that contain only two variables, alpha and beta. We can solve them. So alpha has to be 52 over 17, beta has to be negative 12 over 17 to satisfy both constraints. Now we have the values of alpha and beta. We plug them into these expressions of x, y, z, and u. We get the values of x, y, z, and u. And then we can determine the minimum value of this function under these two constraints right here. Of course, you can try some other combinations. You will get a value greater than this. In sum, to minimize or maximize a function under a constraint, g is 0, we need to set a Lagrangian. L is the function to be optimized minus a Lagrange multiplier alpha times the constraint g. G is always 0, therefore L is equal to f. Then we obtain four equations by setting dl over dx is 0, dl over dy is 0, dl over dz is 0, dl over du is 0. Using these four equations and also using this, we can solve for alpha, x, y, z, and u. Because we have four equations here, we have another equation here, we have 5 equations in total, and we have 5 variables. So we can solve for the values of alpha, x, y, z, and u. And usually we just express x, y, z, and u in terms of alpha and then plug into the constraint over here and solve for the value of alpha first. And then we get the values of x, y, z, and u. So anyway, this is pretty simple. We can just minimize or maximize a function under this kind of constraint. What if there are two constraints? Alright, two constraints, g is 0, h is 0. And then we simply need another Lagrange multiplier. Let's call it beta. L, the Lagrangian, is now the function to be optimized, minus alpha times the first constraint, minus beta times the second constraint. And then we solve this four equations. dl over dx is 0, dl over dy is 0, dl over dz is 0, dl over du is 0. This is to express x, y, z, and u in terms of alpha and beta. And we have two constraints. Remember, x, y, z, and u can be expressed in terms of alpha and beta. Now we have these two equations. We have two equations that contain only two variables, alpha and beta. We can solve those. We get the values of alpha and beta. And then because x, y, z, and u are expressed in terms of alpha and beta, we can then get the values of x, y, and z, and u to minimize or maximize this function f. So this is in general how we use the method of Lagrange multipliers to optimize a function under constraints. In physical chemistry, we use the method of Lagrange multipliers to find the most probable configuration. That means the predominant configuration with the most number of microstates of a thermodynamic system under the constant Ne constraints. So what if we have an isolated system, we have a bunch of molecules with a constant energy, and then we can find the predominant configuration. We can calculate the associated number of microstates, and then we use that to compute entropy using Boltzmann's equation. Entropy equals the Boltzmann constant times the natural logarithm of the number of microstates. Again, we just use the number of microstates associated with the most probable or predominant configuration. Here is the total number of particles in the system, and E is the total energy of the system. We're assuming we have many energy levels, epsilon 1, epsilon 2, epsilon 3, etc. And we're going to assume in epsilon 1 we have A1 particles. In energy level epsilon 2 we have A2 particles. In energy level epsilon I we have AI particles. Therefore, N is equal to the sum of AI, and E is equal to the sum of ai times epsilon I.